There's a planet in our galaxy, orbiting its star at 650 times the Earth-Sun distance. If you placed our entire solar system there, Sun, Neptune, everything, you wouldn't even cover 10% of the way. Our best models of planetary formation simply cannot explain how it got there, and that's far from the only case. For a long time, we thought we had a pretty solid grasp on how planets form. A star is born, a disk of gas and dust swirls around it, grains clump together, rocks collide and merge, and after a few million years, you've got a solar system. Clean, ordered, predictable. Ours was the template. And then we started looking elsewhere. Since the 90s, we've confirmed over 5,700 exoplanets, and a deeply unsettling fraction of them have no business being where they are. Gas giants pressed right up against their star, planets orbiting backwards, worlds circling radioactive stellar corpses, planets less dense than cork, and at least one planetary object so far from its star that gravity alone can't explain it. What we found is that our solar system might be the exception, not the rule. Let me introduce you to the first gut punch. In 1995, Michel Mayor and Didier Queloz announced the discovery of the first exoplanet around a Sun-like star. It's called 51 Pegasi b. It's a gas giant, roughly half the mass of Jupiter. That alone is exciting. The problem? It orbits its star at 0.05 astronomical units. For context, Mercury, our closest planet to the Sun, orbits at 0.39 AU. 51 Peg b is 8 times closer to its star than Mercury is to ours. Its year lasts 4 Earth days. Its surface temperature approaches 1,000 degrees Celsius. And gas giants don't form there. It's not possible. There isn't enough solid material that close to a star to build a planetary core large enough to capture gas. The physics is unambiguous on this. So how did it end up there? The answer we developed is called planetary migration. The idea, the hot Jupiter formed far from its star, where there was enough ice and rock, probably at 5 to 10 AU. But by interacting with the gas disk still surrounding the young star, it bled orbital energy and spiraled inward, slowly at first, then faster. And here's what I need you to understand about what that means for a solar system like ours. When a gas giant migrates inward, it doesn't just move, it devastates everything in its path. It ejects smaller, rocky planets from the system, scrambles their orbits, clears out entire zones. Simulations show that in most systems with a hot Jupiter, any potential for life on inner planets was eliminated or made impossible before it ever had a chance to begin. Our own Jupiter almost did the same thing. The grand tack simulations suggest it migrated inward all the way to where Mars orbits now, then got stopped by Saturn, and both of them drifted back out together. If Jupiter had kept going, Earth would probably not exist in its current form. We got lucky. A lot of systems didn't. Here's something more unsettling. In 1992, before Mayor and Queloz, a Polish astronomer named Alexander Wolszczyn announced the discovery of planets orbiting PSR 1257+12, a pulsar, a rapidly spinning neutron star, a dead star, with planets in orbit around it. What's disturbing isn't just that they exist, it's what they survived to get there. When the parent star went supernova, it released an almost unimaginable amount of energy, enough to sterilize everything within light years. Any planet that was orbiting there would have been either flung out of the system entirely or hit with radiation that would make our nuclear power plants look like nightlights. And yet, these planets are there.
Two theories coexist. Either they survived the explosion, which is already extraordinary, or they reformed afterward from the debris of the dead star in a second accretion disk. Planets born twice, in a sense, built from the ashes of their own system. But the most striking case is different. PSR B1620-26b, nicknamed Methuselah, is a planet 2.5 times the mass of Jupiter orbiting a binary system, a pulsar and a white dwarf. Its estimated age is 12.7 billion years. The universe itself is only 13.8 billion years old. This planet is almost as old as everything. It formed at a time when the universe barely had enough heavy elements to easily build rock. It existed when the Milky Way was still young, and it's still there, orbiting two dead stars, quietly, while we try to figure out how that's even possible. This one I love because it challenges something very basic. We all learned that rocky planets are dense. Earth sits at 5.5 grams per cubic centimeter. Gas giants are less dense. Jupiter is 1.3, Saturn is 0.7. It would float on water if you found an ocean big enough, which remains one of my favorite facts in astronomy. And then there's TRES 4b. TRES 4b is a gas giant about 1,400 light-years away. Its mass is roughly 0.9 times Jupiter's, but its diameter is 1.7 times larger. That gives it a density of about 0.2 grams per cubic centimeter, roughly 1/3 the density of cork. I'll be honest, I checked that number several times. Its interior structure matches nothing in our predictive models for this type of planet. It's close to its star, which heats and puffs up its atmosphere. That part is expected. But even accounting for that, the standard models predict a significantly smaller planet. The excess size remains unexplained, and TRES 4b isn't alone. We call this whole category inflated planets, a dozen or so hot giants whose radii blow past every prediction. Several mechanisms have been proposed: tidal dissipation, magnetic fields, atmospheric currents redistributing heat inward. None of them fit cleanly across all cases. The physics governing these objects is simply not well understood yet. HD 106906b. Back to the planet I mentioned at the top, because this is where it really gets complicated. HD 106906b is an object 11 times the mass of Jupiter, orbiting its star at 650 AU. To give you some sense of scale, Neptune orbits at 30 AU. Voyager 1, after more than 45 years of travel, is about 165 AU from the Sun. HD 106906b is nearly 4 times farther than that. At that distance, the star's gravity is extremely weak. Standard planetary formation models, core accretion or gravitational instability, simply don't produce planets at 650 AU. The protoplanetary disk doesn't reach that far. The leading hypothesis, it formed much closer in, around 10 to 20 AU, and got kicked outward by a gravitational interaction with another giant planet, like a billiard ball sent to the far end of the table. But for it to stay bound to the system, instead of becoming a completely free-floating rogue planet, something else had to anchor it. Neighboring stars passing close by millions of years ago may have perturbed its orbit just enough. What makes that scenario both compelling and uncomfortable is that it requires a precise chain of coincidences to work. And it raises a bigger question about what we call rogue planets. Planetary objects completely ejected from their systems, drifting through the galaxy with no star. We estimate there could be billions of them in the Milky Way alone. Planets in permanent, complete darkness. No sun, no seasons, no light of any kind. Some of them might have liquid oceans, kept warm by internal geothermal heat. Wait, I need you to actually sit with that for a second. I'm saving the most cinematic one for last. WASP-12b is a gas giant about 1,400 light-years away. It orbits its star in 26 hours, and since we've been observing it with precision instruments, we've measured something very specific. Its orbit is shrinking, slowly but measurably. In roughly 3 million years, a blink in astronomical time, WASP-12b will have spiraled close enough that tidal forces from its star will tear it apart. It will be shredded, its gas absorbed by the star. But that's not all. Hubble observations showed that the star is already feeding on WASP-12b's atmosphere. A constant stream of material flows from the planet toward the star, like a tear that never finishes falling. The planet is losing mass in real time. It has a tail, like a comet, but at the scale of a gas giant. What we're watching is a planet in its terminal phase, and the fact that we found it in exactly this state, not already destroyed, not still intact, but actively dying, is itself statistically remarkable. Either we got incredibly lucky to catch it in this few million years window, or this type of orbit always ends this way, and there are many planets in this execution corridor that we haven't found yet. The second option is probably right. What 30 years of exoplanet astronomy has shown us isn't just that there are weird planets out there. It's that our solar system isn't a universal template. It's a survivor among millions of different configurations, some of them violent, unstable, or flatly impossible according to the theories we had. Gas giants that migrated inward and devastated everything in their path. Planets born from the ashes of a supernova. Worlds less dense than wood. A planetary object at the edge of interstellar space that we can't fully explain, and a planet being slowly devoured by its star while we watch. And all of that with just over 6,000 confirmed planets. There are estimated to be hundreds of billions of them in the Milky Way alone. What we don't know yet dwarfs what we do. If you want to go deeper on any of this, planetary migration in our own solar system, the physics of inflated planets, or what rogue planets mean for the possibility of life without a star, let me know in the comments. And if someone you know would get something out of this, send it their way. Take care, and I'll see you in the next one.